Okay, let's try to get this done. It's 6:19. This is video 137, and this is really part two of special cases, which, as I said, really refers to perfect squares. Such an important topic in freshman Regents math. So I'm going to show you a rectangle here, and one side is some number plus 2, and the other side is the same number minus 2. And this configuration makes the middle terms go away, as was explained before, and it's of particular interest to the Regents. Okay, so I'm going to FOIL this out, and I'm going to come up with something that will match what this does. And we might as well give these guys names, since it is a special configuration. These are called conjugates, and that's just trying to say that the second terms are opposite and the first terms are the same. You don't have to know that for the Regents. I don't even know if you have to know that for the Regents, but we have to name things. And like I said, the attraction here is that the middle term goes away when you FOIL them. So I'm going to do that, and then I'm going to go backwards and get this, and then I'm going to do a couple problems, okay? So this is the format that we'll be looking at, and these are called binomial perfect squares, because the middle term goes away, as previously mentioned. Let me move this over just a little bit here, and I'll FOIL this. I've done it before, I understand that. But we're trying to explain this stuff because this is where kids get in trouble more than any place else. And there's a minus 2x in any order, as we've said so many times. And because these two middle terms cancel, you have this format. This guy's a perfect square. That's because 1 is a perfect square. We talked about that in the previous video. You have to recognize that. There's a 1 there, and it's a perfect square. Obviously, 4 is a perfect square. There's a minus sign between them, and we'll play around with that later, but for now, the easy part is there's a minus sign between them. So this is equivalent to this, which represents the area here with restrictions. This is the textbook representation of these, and now I'll do a couple problems and I'll factor these out because we have to go from here to here. As I showed you before, a couple weeks ago it probably was, or at least a week, 2 weeks ago, and I'll show you that the separation or this grouping method works just fine if you don't see it, but it's just easier to use your intuition and look for patterns. So here's the general pattern of what's going on, okay? So I'm going to erase this, and I'll leave the rectangle out. It's not to be confused with a perfect square trinomial. I mean, they're really different things. But the main thing that a freshman would note is that the middle term goes away. So let's leave this out here, and let's take a look at this algebraic expression. And we're asked to factor this. And so I take a look at it, and the first term's a perfect square, and the last term's a perfect square. So I'm going to do it intuitively, and then I'm going to do it using the grouping method that you know so well. Well, anyway, the square root of 4 is 2, and the square root of 9 is 3. And since they're conjugates of each other, which you're supposed to recognize as the pattern, that's what I get, and that's what most freshmen end up doing when they've been working with these for a while. Key, you must see that these are perfect squares. Key, you must recognize perfect squares. If either one of these numbers is not a perfect square, then there are other circumstances that we'll look at when the math gets a little bit more complicated. Okay? So I did that intuitively. That is, I did that using my knowledge of perfect squares, but now I'm going to do it another way, and I'm just going to do this, that 4 times 9 is 36. Well, the square root of 36 is 6, so it's got to be 4x plus 6x. Oh, of course, minus 6x. Again, what do I have in my head? 4 times 9 is 36, square root of there. And now this should work using our method of separation here. So let's factor it out and make sure we're good. and there's a 2x, and there's a 3. And if I write 2x plus 3, and I can find the number that works here, I'm good. But of course the negative 3 works, as we suspected that it would. And the middle terms become this when I use the distributive property. And again, it's been done so many times in this course. There are the 2 conjugates, again, in any order. So this is the factorization of that. And they really love that, I'm warning you, okay? You should definitely be aware of this configuration. Now I'm going to do a slightly more complicated one. And again, notice that when they put in the perfect squares, you might want to use the intuitive method I taught you before, because when you start multiplying big, like 25 times 36, things of that nature, which we'll do, it's to multiply the first times the second and try to figure all that stuff out, may be confusing for a lot of kids. Okay? So now, I'm going to do one, and I just want to show you what happens, that it works both ways, and that you really got to keep an eye always on the coefficients that you're doing. Let's try this one, 9x squared minus 36. And no one's going to deny that 9 and 36 are perfect squares. So the right way to do it, or the intuitive way to do it, as I've said so many times, is the square root of 9 is 3. There's my x. Square root of 36 is 6. And now write the conjugate. Now, there are problems with this, and I wonder if any of you see what the problems are, okay? But I'll speak, since we're not in class and we can't do this in all essential feedback, 3x and 6 are not coprime. You should take a good look at that. So this needed to be factored. This needed to be factored, completely factored. And in fact, if you look at it, 9 goes into 36 4 times, and they're going to ask you, the Regent's going to ask you to do that a lot. So to make this work, I have to factor out the 3 here and the 3 here, okay? And I get 9 times, let's see, that would be 3 times 3, x minus 2, x plus 2. Let's make sure we got that back. There's the 9, and we'd have that back, so this would be this. And then the 9 would multiply that. So let's say we didn't see that. By the way, this gives you back this. And so this is part of what we learned about what we learned about complete factoring. And again, on the Regents, you're going to see a lot of stuff like that, so we'll practice it. Now, I'm going to do this using the separation method now, or the grouping method. And here we go again. 3 times 6 times 2 is 18. And of course, we double the 18, right? So it's plus 8 minus 18x. In any order. I keep saying that, but some kids think it matters, so I have to fight back against that mistaken idea all the time. And what factors out here? The 9x, excuse me. Okay, the 9x, and then you get x plus 2, and you write it again, x plus 2, and what works over here, the negative, let's see here, there's 9 plus 2, and let's see, let's see here, the 18, there it is, okay? Almost had to give up there, and so that means that you have 9x minus 18 times x plus 2. But then you factor out the 9, and you have it all over again, x minus 2 times x plus 2. So again, when you saw me stumble just a little bit there, because I was looking for things, all right? And you see how the math works like this. And I showed you some examples here. I went over the idea with you. And my idea is to sort of give you practice, and then we can work out a lot of these problems together. Most of the practice, by the way, will make it from the Regents book. And so there's the last one that I did. And just one more point that I made before. I'm not going to do the problem, I'll just point it out. Say the coefficient was 16 here and 49 here. We agree these are perfect squares, but 16 times 49, that's a big number. You have to use perfect squares to make this thing work. And to write this out formally the way I just did it is a waste of time once you basically understand it. It's just to show you that it always works and that they're really big on complete factoring with these guys. We'll talk more about that in the next video.